All right, welcome everyone. Let's get started. It is a great pleasure to host Shyam Shankar today, who's from the University of Texas at Austin and who's a longtime friend and collaborator of ours. So Shyam got his PhD from Princeton, I think working with Steve Lyon, if I remember this correctly. Then he joined Yale as a postdoc in 2010. In 2010, he worked there with Michel Deveray predominantly, and yeah, during his stay there, he was really sort of a driving force behind everything that superconducting quantum circuits can do almost. Okay. So from gates to measurement to error correction to remote entanglement, you name it, Shyam has done it. So yeah, one of the main things we've always been focusing on is sort of the aspect of quantum limited measurement. So what are the fundamental limits of measurement? And yeah, that's why we're pleased to have him here today and talk about exactly that. In particular, what are the limits on amplifiers that you can physically realize? So Shyam stuck around at Yale for quite a while until 2019 as a research scientist, where he was basically sort of a leading figure with guiding many grad students on their way. And now, since 2019, he's at UT Austin in the Department of Electrical and Computer Engineering, where he started his own group. And we're really happy to have him here. So let's all welcome Shyam.
Thank you. Thank you. I hope everyone can hear me okay on the audio. Thank you, Wolfgang, for that very nice introduction. And thank you to everyone I've had a chance to chat with already during this visit, and look forward to chatting more after the talk. So I'm going to tell you about how we build Josephson parametric amplifiers. These are essentially microwave frequency amplifiers that work essentially the lowest noise amplifier that you can build at these frequency scales. I'm going to tell you about how they are useful for the measurement specifically of solid-state qubits or superconducting qubits, though these are relatively general purpose devices that could be used for many other types of experiments that happen in sort of a cryogenic environment. As Wolfgang said, I was for a number of years in the group of Michel Deveray at Yale. And so today I will tell you a little bit about some work that we did in his group that I led, along with these postdoc and graduate student colleagues. I've been at UT Austin since 2019. And so I will tell you a little bit about some work that we are doing with a couple of graduate students there. And we collaborate quite closely with the group of Javad Shibani at NYU, who provides us some material to build Josephson junctions. And towards the end of the talk, I'll tell you about that work as well. So just outline. So I'll begin, since taking this more in a colloquium style. I'm guessing many of you are from Wolfgang and Angela's groups, but also many others are here. So I'm going to sort of motivate why we want to build Josephson parametric amplifiers by introducing sort of the basics of superconducting qubits and the measurement of them. And then talk about two specific amplifiers that we have built. The so-called Snail parametric amplifier, which is an amplifier that works at the quantum limit, and in particular has been optimized for making a very high compression power in order to be able to measure signals coming from many qubits. And then in the last part of the talk about a parametric amplifier we are working on at UT, which is based on a new sort of basic junction technology, which is this aluminum indium arsenide superconductor-semiconductor heterostructure material system. Okay. I guess I should say, feel free to stop me at any time. If you have a question, I'm happy to answer during the talk as well. Okay, so just sort of to begin, I think many of you probably know that measurements are sort of an essential prerequisite for quantum technologies. You really need to be able to measure quantum systems very well. If you want to make a large-scale quantum computer, for instance. So what is a quantum measurement? Very abstractly, we can think we have some two-level system or a qubit which has two energy eigenstates, ground and excited. When we want to measure it, we couple it to some other device that we typically call a meter. So that's this device on the right. And this meter has two states that we call 0 and 1. And what we mean by a measurement is that we couple our qubit to the meter such that if the qubit is in the ground state, the meter lights up as 0. And if the qubit is in the excited state, the meter lights up as 1. And we want to be able to do this process very well. In particular for quantum computation, this measurement process is necessary if we want to be able to initialize our qubit in a definite state, like the 0 state. At the end of a computation, you want to be able to read out the states of our qubits, and so you need this process again to do the readout. And this measurement process is also crucial for quantum error correction. As I'm sure many of you know, quantum bits tend to be very error prone. And so we need to do some kind of error correction process to correct the errors that seem to keep occurring on our qubits. And so the way we do that is we try to measure, is there an error? And then we, using some measurement process, and then we apply some feedback to correct the error. And so being able to do a good quantum measurement is going to be crucial even for that. Okay, so what are some of the requirements of a good quantum measurement? The first one is high fidelity. We want that the outcome is an accurate representation of the state. So if I am in the ground state, I want with very, very high probability to be getting an outcome 0. If I'm in the excited state, I want with very high probability to get an outcome 1. So that's sort of just given. The other property that we want is this property that's called quantum non-demolition, which is sort of a reverse of what I just said. We want that the state of the quantum system after the measurement should be an accurate representation of what the outcome was, right? So if I got an outcome 0, I want the state after the measurement to be the ground state. If I got the outcome 1, I want the state after the measurement to be the excited state. And so that's actually not trivial. That we learned that in our undergraduate quantum physics as the basic postulate of projective measurement, but it's not trivial to actually realize this in the lab. A very common type of quantum measurement you may be familiar with is knowing whether there's a photon or not in an optical fiber, for instance. And so you let the photon hit a photodetector, you get a click, you know therefore that there is a photon, but after the measurement, the photon doesn't exist anymore, right? So that's very much not a quantum non-demolition measurement, even though that's a very standard measurement that we can do in the lab, right? So engineering a kind of quantum non-demolition measurement, which is also high fidelity, is non-trivial, but it's quite desirable if you want to do a large-scale quantum computation. And then finally, sort of goes without saying, I guess we would like our quantum measurements to be fast, such that the general rate at which we do these measurements is faster than the rate at which errors occur, for instance. So we want high-speed measurements. All right, so I'm going to work in this framework called circuit QED, where basically we couple artificial atoms, which are usually some kind of solid-state system, potentially with discrete energy levels, just like real atoms. We couple them to the modes of a microwave cavity and use that for manipulation and readout. So the various types of artificial atoms that we could measure in this type of framework, I will be specifically talking about superconducting Josephson qubits. But there are many other condensed matter systems, quantum dots, nanowires, and 2D electron systems, just as examples that have been manipulated and measured in this framework. So when you want to manipulate the state of your atom, you may drive with microwave frequency pulses at the transition frequencies of the atom. And when you want to measure the state of the atom, you will typically drive the resonator that's coupled to it and look at the transmitted response. And the transmitted response will tell you something about what is the state of the atom. So that's the basic framework. Okay. The specific Josephson qubits that I work with I should just give a short, brief introduction to them for those of you who are not so familiar. The Josephson junction that I'm going to be building are essentially made out of two pieces of superconductor, typically aluminum, separated by a thin oxide barrier. And this device basically behaves as a parallel combination of a nonlinear inductor and a capacitance. The capacitance arises because you have two metals, aluminum, separated by a thin gap. So that's a capacitor. And the inductance arises from the tunneling of Cooper pairs between the two superconductors. You can understand that by looking at this current flux relationship, where phi, the flux, is just the time integral of the voltage across this device. If you sort of Taylor expand this to first order, you get I equal to I naught phi, which is the current flux relation of a standard inductor, phi equal to Li. But when you see the Taylor expansion, you have, of course, higher order terms in the Taylor expansion. And those higher order terms basically make this behave like a nonlinear inductor. So this is an example of an SEM image of an aluminum tunnel junction for a characteristic size of about a micron. The so-called critical current I naught, which sets this inductance scale, is about a microamp. And you can express the inductance as a function of the current through the device by this sort of power series that I show. So the key point is that this is a nonlinear inductor with very, very little dissipation, which is very, very hard to get practically in any other system. The fact that it's a superconductor means that it's essentially very little resistive loss as compared to the value of the inductance. All right, so that's the basic device element that we will use. Towards the end of the talk, I will tell you about some other types of Josephson junctions where instead of having an oxide in the middle, we will replace that with semiconductors and show how there are helpful properties of such a super semi Josephson junction when you look at this type of inductance, nonlinear inductor, and using it in circuits. Okay, the specific superconducting qubit we will be using is a so-called transmon qubit. You take the Josephson junction and shunt it with some big capacitor, such that if you look at the potential energy of this circuit as a function of this flux coordinate, it is a anharmonic potential energy, which when you quantize, you get discrete energy levels with unequal spacing, such that the lowest transition of roughly 5 gigahertz is going to be the 2 levels qubit that we will be using. And the typical error timescales in this type of device is of the order of 100 microseconds, though it's even become longer in the last few years. Okay, and so here is sort of a practical example of a circuit QED system that we build in our lab. We take our Josephson junction. This is a slightly different looking Josephson junction from before. There are again 2 layers of aluminum separated by a thin oxide barrier over there in that overlapping region. It's connected to 2 big pads that form the capacitor of my transmon qubit. And then all of that is sitting on a sapphire chip that's placed inside a microwave shoebox style cavity. So it's a rectangular microwave cavity that has finite modes at various frequencies. Typically, we can make the frequency, let's say, around 8 gigahertz. And we can drive the modes of the microwave cavity via microwave cables on the input side and look at the transmitted response on the output side, such that when everything is cold in a dilution refrigerator, we can describe the system with this so-called Hamiltonian. It consists of a harmonic oscillator term related to the cavity, the fundamental mode of the microwave cavity. This is omega A dagger A. We have this anharmonic oscillator that represents our transmon qubit. And then there is this coupling between the cavity mode and the transmon qubit mode, which we call chi. This is what we call the dispersive shift, and will be the property of this circuit QED system that allows us to do a quantum non-demolition readout. So how does that work? So essentially, you can rewrite that Hamiltonian I just showed you in this form. And when you stare at it, you see that essentially the frequency of the cavity, which is represented by the stuff in the bracket in front of the A dagger A term, depends on the state of the qubit, which is represented here by the sigma z operator, which can take either +1 or -1 value. such that the frequency of the cavity shifts by basically chi when the qubit goes from the ground state to the excited state. And so if you do look at a transmission through this cavity, you get two basic frequencies. It behaves as if, as the qubit goes from one state to the other, it behaves as if you're sticking a piece of dielectric into the cavity, and it has two different dielectric constants such that the frequency is shifting. Okay, and so we have a response of the cavity, typically a Lorentzian function with at the ground state, and shifted by chi in the excited state. Typically, value of chi is a few megahertz, which is roughly equal to the width, the line width of this cavity set by these coupling to the transmission lines, which is of the same order, and that's what this value kappa represents. Okay. All right, so let's try to understand how we do what really sets the fidelity of a qubit readout. So we have these two responses for the cavity when the qubit is in the ground and excited state. We drive the cavity at this frequency right in the middle. We can represent the state of that input microwave pulse on the in-phase quadrature plane by a coherent state alpha, which has some amplitude, as well as a Gaussian fuzz that may be hard to see on the projector, which represents sort of the noise associated with a coherent state when you measure its two quadratures. Okay, so when that readout pulse goes through the transmits through the microwave cavity, if the qubit is in the ground state, you see that it gets one phase shift represented by the blue point where my arrow is. And if the qubit is in the excited state, it gets a different phase shift. And so that corresponds to taking this coherent state and rotating it either clockwise or counterclockwise, such that at the end, you get overall phase shift between the two states represented by this symbol phi, which is essentially the difference at this drive frequency. Okay. And so now the question is, what sets the fidelity of this readout? You can see that I can draw in principle a line on this IQ plane and associates outcomes to the left as being qubit in ground, outcomes on the right, qubit is in the excited. And so the question of how well can we discriminate these two qubit states naturally arises. It's related to how separate these two distributions are as compared to their width, which is set by the noise level. And what sets the noise level? It's basically set by what detection electronics we use at the output of our superconducting cavity to process the output microwave signal, right? And in particular, it depends on how noisy is this amplifier that is used to process this output microwave pulse. Okay, so this is sort of maybe something that is electronics 101, but maybe we should just review what exactly is an amplifier doing. An amplifier takes an input signal and produces a larger copy, so it provides power gain. But it takes any input noise and also provides a larger copy of the input noise. So in a sense, there is a corresponding gain in the noise as well. But the sort of not so nice thing about a standard amplifier is that it always adds some extra noise to the signal on its output. Okay, and so if you just look at the SNR at this level, the SNR is actually becoming worse. So, and this is a fundamental law of nature, as I will describe. But so why would you ever want to use an amplifier? The reason is that there is always some following detector, like for instance, an analog to digital converter in your computer, which you're going to use to record this microwave signal. And the purpose of the amplifier is to boost the power of the signal and any other noise much above the following detector noise, such that the detector noise can be thought of as being inconsequential. And so this naturally raises a question of a concept of efficiency. How small can we make this SNR degradation that comes right out of the front in order to make this detector noise to be inconsequential. And so naturally, you would want to use an amplifier that adds the minimum amount of added noise in order to measure the signal. And so that suffers the least possible SNR degradation, right? Okay, so there is this is well understood now since sort of the late 1960s, and was formalized by a theorem that's called the Caves theorem, written out in 1982. It says that if you take a phase-preserving amplifier, which is basically the type of op-amp amplifier that we learn about in sort of undergraduate electrical circuits classes, and you look at the input signal, you can represent that by a coherent state. It has this sort of vector whose amplitude is related to the photon occupancy of that pulse. We represent that by square root n. The noise, which is represented by this Gaussian distribution about that mean value, is actually 1/2 in these units, which I will represent this as square root of half times a half for a bit. If you look at the output, basically the length of that vector is amplified by a factor g, where g is the power gain, so the amplitude goes up by square root of g. The noise also blows up by this factor square root of g, but in addition to the original half, we get this extra factor of a, which is called the Caves added noise number. The minimum value of the added noise number is 1/2 for large gain. Electrical engineers often use an alternative specification called the noise temperature, which is the added noise photon number, but expressed as a temperature using HF over KB. And so this thing that says that the minimum added noise A is 1/2 is what is called the standard quantum limit of phase-preserving amplification. It says that the ideal quantum limited amplifier adds exactly 1/2 photon of noise. It basically comes down from Heisenberg's uncertainty principle. You know, in Heisenberg's uncertainty principle that if you try to measure 2 quadratures of a harmonic oscillator, X and P, simultaneously, you will necessarily add some noise. And the minimum value of that added noise expressed in this form is basically 1/2 a photon. And essentially, that's exactly what we are doing when we're trying to measure 2 quadratures of an electrical signal arising from some source, which is in a coherent state. Okay, so this is how the added noise shows up. And so now when we look at our distributions for these 2 G and E coherent states, basically the noise level on this distribution corresponds to basically about 1/2 a photon, and any inefficiency over and above that because of, let's say, detector noise shows up as a standard deviation, which is slightly bigger than the quantum limit. So if you look at sort of what can you just buy commercially, typically we use these semiconductor HEMT amplifiers that have been built over the number of years. They sort of have a noise temperature or added noise photon number of roughly 20 photons in these units. And the Josephson parametric amplifiers that I hope now have motivated you for why we want to build them, those essentially have a photon number added noise of roughly 1/2 to 1 photon. And the fact that this is an order of magnitude better is what's really responsible specifically for superconducting qubits for us to be able to measure qubits with essentially 99% or more accuracy, fidelity, and also nearly 99% quantum non-demolition in a time scale of a few hundred nanoseconds, which you can compare to the sort of error time scales of few hundred microseconds or so that I was telling you about earlier. Okay, let me just pause and make sure there was no questions. All right, so now let's move on to talking about some specific examples of these Josephson parametric amplifiers, in particular the Snail parametric amplifier. So I've already used this word parametric amplifier a few times. What is what is this physical phenomenon? Essentially, you have already experienced this yourself, or if you have a child. If you play on a swing, you know that if you move your body in a periodic fashion, you can essentially amplify the oscillation. That's essentially what a parametric amplifier does. what is happening here in this example is that you're changing the moment of inertia of this oscillator in a periodic fashion. And that is responsible. That's why we call it a parametric amplifier. The moment of inertia is the parameter of this oscillator. You see that with this type of phenomena, you need two things. One is this so-called pump, which is a source of energy. If you want to amplify an oscillation, you need to be inputting energy into the system somehow. And in this case, for instance, it's the fact that the child has to do work against the centrifugal force in this oscillation. And in the same way, you'll see in our params, we have to supply some power, some energy. The other thing you have to see is that this oscillator has to be nonlinear. If it's a purely linear, simple harmonic oscillator, you're not going to get this amplification physics. In this case, it's the fact that the restoring force goes as sine theta. Right? And that's essentially where the idea that the Josephson inductance is a nonlinear inductance comes in. All right, so I don't want to scare you, but there are a whole variety of Josephson parametric amplifiers that people have built coming from many, many different groups. This is just a picture taken from this recent review. I don't suggest that you have to go into that, but essentially this is a field that's been around for a while. It actually originates from people building diode-based parametric amplifiers in the 1960s. The way you can think about these amplifiers is that they're typically, as the circuits become more complex, they have more and more ports. So the transmission lines that you hook up to the device, to the circuit, you can have two different styles where they're either degenerate or non-degenerate. These refer to the number of microwave modes in the structure. And then finally, the thing that is important is to see that there is this distinguishing feature with you use a 3-wave mixing style nonlinearity or a 4-wave mixing style nonlinearity. That's referred to here as 3W and 4W. So the two amplifiers I'm going to talk about are basically one-port degenerate 3-wave and 4-wave mixing amplifiers. Those are the simplest circuits up here, and we'll see a little bit more about them going forward. Okay, so what is it that we are trying to achieve when we are sort of building these params in practice? So I already told you why that they get very low added noise, but so let's look at this SNR equation. So the SNR of your readout is going to be the signal minus any loss going from the output all the way up to your detector. But if you have enough gain in your amplifier, you can reduce the effect of the loss that you might be having up when you're going up to the detector. On the denominator, you have the noise that came with the signal. You have the added noise of the amplifier. Plus, there might be more noise in the rest of the detection electronics, but that gets divided down by the gain of the amplifier. And so if we want to boost the SNR, essentially we want large gain, roughly about a factor of 100 in practice, so that these last two factors are minimized. We want near quantum limited added noise. That is, we want this factor at the bottom to be as small as possible. And so these are two key things that params give you. But then further engineering comes in, because in practice, we may want to be able to measure a very large signal. Right? So for instance, if you have many, many qubits that you're trying to measure simultaneously, the signal from all of those qubits may be coming out at your amplifier at the same time. And so you want to be able to handle all of that power such that this equation is valid, even with multiple qubits being measured. And that's important for scaling and also for many other applications. The other thing you want is that this whole expression is a function of frequency at which you're doing the measurement. And so you would want ideally that you can amplify over a large frequency range if, again, you want to measure signals from many qubits. And there may be other things that you may also want from your parametric amplifier that are just sort of added bonus. Okay, so the device that I'm going to talk about, this Snail parametric amplifier, is built on a circuit, composite circuit element that's called the Snail. It's a loop consisting of a single Josephson junction shunted by 3 Josephson junctions, which are bigger. The factor alpha is the ratio of the sizes of the junctions. And so on the right is a SEM image of a typical Snail. consisting of a single junction and 3 larger junctions. This circuit shows up so much in our experiments and in many other groups' experiments that we decided to give it a symbol. It has its own symbol that you will see now used repeatedly, and we called it a Snail, standing for superconducting nonlinear asymmetric inductive elements. So you may have, if you're familiar with Josephson circuits, heard about the squid and the slug. So that tells you that we like to name our composite circuits after crustaceans. And so we decided to give it a name as well, and it kind of stuck. So that was nice. All right, so how does this snail behave? If we can look at the sort of energy of this circuit as a function of this flux coordinate, we can write that out over here. We don't have to look at that so closely. You can just Taylor expand this, and you see that it has a phi square, phi cube, phi to the 4th term, which you can see if you just look at this potential energy as a function of flux. You can see that it's slightly canted. It's not symmetric about the center, about the minimum, and that tells you that there is, in addition to sort of the parabolic term here, you have a cubic term and a quartic term in the Taylor expansion. Okay, so we are going to show you now that this cubic term is what is sort of very useful, and this quartic term is what is ideally is a parasite. We don't want it. Okay, so I'm going to show you how we can engineer those two. Okay, so the device we built, this so-called Snail parametric amplifiers, consists of a microwave resonator, roughly lambda by 2 in length, at the center of which we embed an array of these snails. Each snail is the same as I showed you before, but we can have m of them. M is roughly 20. And you can see that at the level of this, the design of the amplifier, we can control various things like the Josephson inductance, the ratio of the sizes of the junctions, the number of arrays, snails in the array, what is the length of these transmission line sections, and also we can control the coupling capacitance, which sets the line width of our device. So all of that is just set when we fabricate the device. This is aluminum on silicon, done with e-beam lithography. And inside the device, when it's cold, we can set the flux through this loop to control the snail as well. Yes. So as I will tell you now, basically all these knobs are what we can use to control the Hamiltonian of the device. And so essentially a combination of all of these parameters, the potential energy that I showed over here, all together end up in a certain Hamiltonian for this device. And in this Hamiltonian, you can see that in addition to that sort of harmonic oscillator-like term, there is this so-called 3-wave mixing nonlinear term, G3 a dagger a plus a cubed, and a 4-wave mixing nonlinear term, G4 a plus a dagger to the 4th. They arise from that C3 term and the C4 term of the snail. Okay, and I can control the magnitudes of these various terms and the relative magnitudes by playing with all of these parameters, M and LJ and so on. Okay, does that answer your question? All right, so and what I want to show you now is that with these parametric amplifiers, if we specifically use this 3-wave mixing process and suppress as much as possible the 4-wave mixing process, we can make a better parametric amplifier. Okay. So this is just some data that gives you a sense of the various frequency scales of these terms. So the typical mode is somewhere between 7 and 6 gigahertz. That's the frequency at which we want to amplify. The line width of the mode is typically a few hundred megahertz. That sort of sets the bandwidth of our amplifier. There is this G3 nonlinearity, which is typically about a megahertz. And then there's this G4 nonlinearity, the 4-wave mixing one, which is about a kilohertz. And so you see that we have to really have our engineering well enough to control something like 6 orders of magnitude in energy scales here. And we can do that. And there is this very interesting point that the snail provides. There's essentially an interference in how the current goes through one arm of the snail versus the other, such that at this special flux point, roughly about 0.3 to 0.4 flux quantum, the G4 term can essentially go to 0. It actually goes through 0 and becomes negative, and this is, I'm plotting the magnitude. Okay, yes. Kappa depends a little bit on the magnetic flux because the impedance I'm looking into the 50 ohm environment may not be exactly really 50 ohm across all frequencies, and so there might be some variation. And so that's why that's a hopefully as small as possible variation. Now, okay, so this is sort of the type of device we build. Let's just explain in sort of more quantum mechanical terms how this amplifier works. We have this Hamiltonian. We have this sort of resonance at frequency omega A. We apply a pump at roughly twice the resonance frequency with amplitude alpha p. That means that this three-wave mixing nonlinearity gets converted into an effective Hamiltonian that looks like G A square plus A dagger square, which is basically creation or destruction of a pair of photons. And so what exactly is happening is that if I apply a small signal, that small signal stimulates via the effect of this term the destruction of a pump photon into a pair of photons. One is at the signal frequency, and there is a copy of that also at the so-called idler frequency, where the sum of these two frequencies adds up to the pump for maintaining energy conservation. Okay, so as a result, when you apply an incident small signal, you get more photons coming out of the device as compared to what you put in, and therefore you have gain. Okay, and so if I sort of look at an example of the gain of the device as a function of frequency, essentially there's a formula that you can write out, and the denominator in this formula has this sort of point where the denominator goes to 0, and so the gain essentially can go to infinity in principle. And this is sort of in practice that you can get easily 20 to 40 dB of gain over a bandwidth of usually about 10, 20 megahertz in the best devices. Okay, but this type of behavior cannot be true as I increase the signal power, the incident signal power, simply because I'm applying a definite pump power, which is setting the energy source for the amplification. As I turn up my signal power, I'll be asking for more photons to come out of the device than the amount of pump photons I'm supplying to the device. Right? So this kind of physics cannot be going on arbitrarily to any arbitrarily large signal power. And so practically what we see is that if you look at as a function of the input signal power, the gain of the device sort of drops. And this point, which we call the 1 dB compression power, is the point at which the gain has dropped by 1 dB. And in typical sort of params before this work, this number was in the range of minus 130 to minus 120 dBm, which corresponds to roughly about 1 photon to 10 photons at these frequency scales. Even in the best devices, maybe only 1 order of magnitude better. And that corresponds very closely to the sort of power that we typically use for measuring our qubits. And so the amplifier essentially was limiting the number of qubits you could build. So why does this physics happen? Essentially, it comes from this G4 term of the Hamiltonian, the 4-wave mixing nonlinearity. One way to understand that is that in this denominator, the delta, the detuning, corresponds to the frequency of the mode. And as you increase the power, this 4-wave mixing nonlinearity shifts the frequency of the mode. It's called a Stark shift. And so the gain essentially falls. You're no longer at that point where the denominator is 0, and so the gain falls. And so it boils down to there is a relation between the 1 dB compression power and the 4-wave mixing nonlinearity, which, as I told you, is a sort of a parasite. We don't want it. And so the whole name of the game and the really crucial thing that the Snail provided to all of this work was the idea that we could actually control the various nonlinearities and engineer them. And so this is some data from some work a few years ago, which showed that as over a broad range of devices with different designs, changing line width, as well as the 4-wave mixing nonlinearity that we can engineer sort of with the knobs that I told you earlier that we can control, we showed that indeed you can improve the compression power from sort of the first generation device by almost 2 orders of magnitude. And so now this sort of minus 110 is sort of a very standard number. And on top of that, if you are careful with the tuning, you can actually get a peak in the compression power that corresponds to exactly the point where this G4 nonlinearity goes to 0. Okay. And so now the name of the game going forward is, can we make this range of frequency much broader? Okay, so that's what I want to say about the Snail parametric amplifier. This is now work from a couple years ago. In more recent times, I want to show you how this device can be used not just as a parametric amplifier, but as a very good source of quantum light. So let's just understand what happens when we just have only noise entering the device. This exact same process means that there will be noisy signals coming out of the device at this signal and idler frequency. That's when there is some incident signal frequency noise. If there's noise at the idler, there is again the same process that happens. And so you can see at the signal frequency, there is double the noise that comes out of the device. This is exactly related to that extra half a photon of noise that I told you a paramp adds. But then these two copies of the noise are highly correlated, such that if the signal and idler frequencies are exactly aligned, the noise adds up along one quadrature and subtracts along the other quadrature. And you basically get what is called a single mode squeeze state. There's an equivalent kind of correlated state that also comes out even when the noises are, when the frequencies are not the same, and in which case it's called a two-mode squeeze state. So if you look at the IQ output of the device, you have basically, if you have the input being in a vacuum state, the output is in a so-called squeeze state where one quadrature is amplified and the other quadrature is squeezed. And so the sort of figure of merit of this type of work, this amplifier, is how much can you squeeze one quadrature with respect to the other, because this type of device can now, squeeze states can be used as a very good input state for other types of sensitive measurements, including qubit readout, but also very many other types of applications in quantum sensing. So the basic understanding of why does a squeeze state get not infinite squeezing is the fact that there is this Kerr nonlinearity or four-way mixing nonlinearity. That means that as you try to increase the squeezing, there is a distortion that shows up at very, very high squeezing, high pump amplitude. And so the fact that with our Snail, we can actually engineer the four-way mixing nonlinearity as compared to the three-way mixing one, and for instance, operate near the Kerr-free point, means that we could potentially improve the quality of the squeeze states that we can produce out of this particular type of param. And so this is some experiments that we are recently underway, which is ongoing, that you can see as a function of the input pump amplitude, you get a pretty highly squeezed state. The noise in one quadrature is less than the noise with the pump off, and the noise in the other quadrature is quite a bit larger. We can express by looking along these two quadratures this so-called squeezing ratio, and that is plotted here as a function of the pump amplitude and the pump detuning taken near this so-called Kerr-free point. And if I sort of make a cut and just plot the squeezing as a function of pump amplitude, you see this sort of curve where the measured squeezing in our room temperature detection electronics is roughly 1 dB below what it would be if the amplifier is off. Okay, so now I have to sort of distinguish a little bit. This 1 dB has to be compared. What is it being compared to? It's being compared to when the pump amplifier is off. And in that situation, the noise that you're measuring is essentially the noise of the rest of the detection electronics. You can express that in terms of the so-called system noise temperature of the rest of the detection electronics, and the fact that essentially you can think of it as basically I'm cutting down a little bit of my squeeze state that's coming out of my amplifier and adding basically vacuum noise. And so we can, in principle, if we have a very well calibrated measurement system, we can adjust for this squeezing value using this formula and see an observed squeezing that is actually, observed squeezing that is actually much better than this 1 dB number. And so that's sort of what we are working on right now as we're speaking. We are basically trying to calibrate this, the output measurement chain efficiency. We're trying to make sure that the input noise is really vacuum noise as opposed to thermal noise. to be able to give a good estimate of what this 1 dB of squeezing actually corresponds to in terms of the quantum noise coming out, the squeeze state that's coming out of the param. All right, so I have just a couple minutes left. I just want to quickly introduce this new kind of parametric amplifier that we are also building, which is built with this rather different Josephson junction technology. So I already told you a little bit about essentially all the stuff so far is based on these aluminum oxide tunnel junctions. So these are the types of junctions that Ivar Gever won the Nobel Prize for back in the 60s. So it's a very, very old technology. As I said, it has very little dissipation, but it has these naturally some higher order nonlinearities that we can't really get away from. So how could we change that? In recent times, there are these new kinds of Josephson junctions where we have a semiconductor, in this case, indium arsenide, in proximity contact to two aluminum electrodes. And so this forms a super, semi-super kind of Josephson junction. And moreover, you can control the conductivity of the electrons in the indium arsenide using a gate electrode that is separated from the channel. So this looks a lot like a traditional FET, but it's a Josephson junction. We are operating it at 20 millikelvin. This type of junction has naturally a smaller nonlinearity as compared to the aluminum tunnel junction because it's based on a semiconducting channel as opposed to an insulator. It allows you to voltage tune directly the coupling between the two superconductors, so you can control this Josephson inductance using a separate gate electrode. And people have already tried to build qubits with that. They're called gate-mount qubits. And so the question that we have underway is, can we build an amplifier with this type of new junction technology? So here are just a few images of the type of junctions that we built. We get the material from Jawad Shabani's group. They grow up to the epitaxial aluminum layer in an MBE system. And then we fabricate this sort of nanoscale device. We etch out a gap in the aluminum, put down the oxide, and put down a gold aluminum gate. You can see over here an example of the switching current characteristics, the AC resistance as a function of the bias current, where you see basically over some range of bias currents, the resistance of the device is 0, which you expect for a Josephson junction. So that's super current that's showing up over there. But then at some point, you basically switched into the so-called normal state of the Josephson junction. And this switching current gives an estimate of the critical current of the device, which is tunable with this gate voltage. And so now that we have this voltage tunable Josephson junction, we can now build parametric amplifiers of very similar style as before. This is an example of a circuit that would behave like a 4-wave mixing parametric amplifier. We can also apply the RF pump instead to the gate electrode, in which case it would behave like a 3-wave mixing parametric amplifier. This is an example of the device we are building in the lab. Essentially, right at the end, there is this Josephson junction FET. There's the gate electrode coming in from the top right. Inside there is the drain and source electrode of the Josephson junction that is separated by a thin 100 nanometer gap. The rest of the circuit is connected to a microwave matching structure. And we put signals in on the left and look at the reflected signal. That's the image you saw before. And so we've just been able to show recently that we have gain on this device. So when we turn on the pump, we get this amplified signal coming out of the device. It behaves as a function of pump power and pump frequency, like a sort of traditional 4-wave mixing parametric amplifier with different values of the gain. We can also look at the compression power of the device. And in sort of the first generation device, the first device we made, we already got almost an order of magnitude larger compression power than we were sort of expecting from the design. And that is essentially an indication that the nonlinearity in this device is actually quite a bit lower than that coming from a traditional aluminum tunnel junction. And so what we are sort of working on right now, as I conclude, is basically to carefully measure what is the 4-wave mixing nonlinearity directly and use that and then turn on sort of pumping on the gate electrode, use the amplifier in this 3-wave mixing style where the 4-wave mixing nonlinearity is suppressed to make a a high compression power param using this new junction technology. All right, so with that, I guess I should conclude. I hope I have shown you why JPAs are really very nice devices to build for quantum information processing. I spoke specifically about the Snail param, which we optimized for compression power and are now testing as devices that can produce squeeze states of microwave light. And right at the end, told you a little bit about these super semi junction-based params, which are also promising. Thank you.
Thanks very much, Sham, for a wonderful talk. Let's see, do we have questions for Sham? Okay. I guess for the Zoom audience, or you just yell and you repeat it. That's maybe easier.
So, can you compare the degree of squeezing you would make stuff that like Conrad Leonard got for the axion?
Yes, so I think in Conrad Leonard's amplifier.
Can you repeat the question for Zoom audience?
Sure, the Zoom the question was, can we compare the level of squeezing we obtained as compared to what the group of Conrad Leonard obtained, where it was roughly a factor of 3, I think, so about 5 dB of squeezing. We are expecting, based on the calibrations that we have so far, that we are closer to 10 dB of squeezing, but we are trying to be careful with the efficiency measurements.
Okay, let's see, any more? Here.
Right, so the question is, how do you distinguish vacuum noise from thermal noise? And if what do you do to make the thermal noise minimum other than thermalizing the sample? The issue with thermal noise is actually that we have a bunch of coax cables hooked up to our sample, and we are generating a certain amount of microwave pump power at room temperature from room temperature electronics to get a certain amount of pump at the sample, and all of that room temperature electronics may be generating more noise than one would ideally like, more than 300 Kelvin noise. And so we need basically some careful filtering to make sure that any noise that we're introducing at room temperature is not actually basically making the sample hotter, right? So it's not just the fact whether you're thermalizing the device at base, it's also how much noise are you piping into the device from your room temperature detection electronics. And so now the question of how do you distinguish that? One way to distinguish that is using a qubit measurement setup where you explicitly use a qubit and look at basically the dephasing of a qubit and what is the measurement efficiency of a qubit. So that's one way.
Sorry, I got a little lost at the end. Can you speak a little bit to how this gate tunable gate on system is going to result in lower loss at the end of the day? Is it this higher tuning of the C4 factor versus like and
sure.
If you have any idea of where the losses come from.
Right. So so the question is basically, what exactly maybe does the new super semi Josephson junction technology bring into this amplifier work? Does it actually reduce loss, for instance? So I guess I should maybe clarify. It doesn't reduce the loss, but what it does is that it allows you to basically make a source of nonlinearity that is weaker than the nonlinearity that's intrinsic to a traditional aluminum tunnel junction, while at the same time, the dissipation rates are not so high that it becomes too high to be useful. It's always sort of the ratio of nonlinearity to dissipation rate that sort of sets the how good is the device potentially. So this sort of new way of making junctions and maybe follow-ons as the technology improves can potentially allow us to make very good params because they have weaker nonlinearity and therefore improve, for instance, compression power. There is a trade-off between compression power and bandwidth, so we can potentially now get a larger bandwidth for the same compression power and so on. So as you as you imagine, scaling up these systems to large scale, circuits, the fact that we can do this with a more super semi style of device is promising.
So with the indium arsenide junction Snail, you still have 3 large junctions.
Right. So if the question is about whether we made snails with indium arsenide, we did not make a snail. We just make a single JJ. We can make a snail. We can make a loop with the super semi material where there's a small junction and 3 large junctions. But so far we've just been working on a single junction, but it's gate voltage tunable, so that allows you to also do 3-wave mixing. Yes. Yes, that's what this plot was about, or this plot on the top left. Yeah. Oh, sure. Okay, so the question is, what method do we use for squeezing? So we are essentially using the output line of coming from the superconducting circuit. We have a Hempt amplifier at 4 Kelvin that just boosts that incident noise above any following detector noise, and then we digitize the noise coming out of that, and we can plot it along these 2 quadratures. Yeah, it's heterodyne, essentially heterodyne style readout. Yeah.
One last
So the role of the indium arsenide, so the question is, what is the role of the indium arsenide quantum well? Essentially the role of the indium arsenide quantum well is that it's a channel of electrons that can allow tunneling of electrons between the source and the drain electrodes, right? So we have these epitaxial aluminum electrodes. The electron wave function in this electrodes extends down. This is a couple of nanometers. So the electron wave function actually extends into this quantum well. The electrons in the quantum well don't lose coherence as they move from source to drain because the phase coherence breaking length is longer than this couple hundred nanometers. So we can actually get coherent electron tunneling, Cooper pair tunneling rather, between the electrons on the drain electrode and the source electrode. So it's basically a Josephson weak link, similar to the oxide in the traditional junction. In that case, the oxide was a nanometer. Here it's more 100 nanometer scale size structure. Yeah.
All right.
I think we're good on time, so let's all thank Shyam again for a wonderful talk.
Thank you.